Welcome to the deep dive. We're looking at a really fascinating stack of sources today about marine electronics.
Yeah.
We're talking about the complex, often sort of unseen systems that power everything from, offshore cruisers to those high-performance sport fishing boats.
Yes.
And this isn't just about flashy screens and gadgets. It's really about safety, compliance, and survival.
That's exactly right. And I think our mission for you, the learner, is to understand not just what these systems do, but why they're engineered in such a specific, purpose-built way.
Right.
They're just fundamentally different from land-based or even, your car's electronics. They have to survive the toughest environment on Earth, the ocean.
I mean, when you look at the stress profile of a boat versus a car, the differences are they're staggering. A car hits a bump and it's over in a second.
It's momentary, yeah.
A boat is subjected to this constant jarring vibration. It literally never stops.
And that's before you even get to the chemistry of the whole thing. You've got this relentless saltwater exposure, which brings in risks of galvanic and electrolytic corrosion. Then there's high humidity just getting into every single circuit board and these huge temperature swings. 1 minute the sun is beating down, the next a squall hits.
And the thing we can't forget is the power constraint. You're working with limited onboard DC power. We're talking 12-volt or 24-volt systems.
Which just adds a whole other layer of complexity.
Okay, so let's unpack this. Let's start with the foundational engineering.
Okay.
What are the specific design elements that let these devices work for years in that relentless, corrosive place?
Well, it really starts with the basics.
Yeah.
The physical protection.
The casing.
Exactly. The electronics housings have to be completely sealed. They often meet these really stringent IP ratings, like IPX7, which means they can be fully submerged, not just splashed.
Yeah.
But the real difference, I think, is inside the hull. It's in the wiring.
That's the part so many people miss. They just assume, wire is wire.
And that assumption leads to catastrophic failure. It really does. Standard bare copper wire, it just oxidizes so fast in a humid, salty atmosphere. But what's worse, the sources highlight this thing called capillary action.
Okay, what's that?
Salt water can actually be drawn under the plastic jacket of the wire through these microscopic imperfections. And it can cause corrosion kilometers away from where the actual splash happened.
So the wire is literally corroding from the inside out silently.
Precisely. That is why marine systems mandate tinned copper wiring. The tinning is a coating process that just dramatically slows down that oxidation, and crucially, it stops the capillary action.
So it's non-negotiable.
Absolutely non-negotiable for longevity.
So we have these ruggedized components, corrosion-proof wiring, but once they're all mounted and vibrating, they have to communicate. And that brings us to the communication backbone. We're talking about NMEA 2000 and standard Ethernet.
Yeah, and what's fascinating here is how these two protocols kind of divide the labor. It's based on reliability versus bandwidth. NMEA 2000 is the critical workhorse. It uses a controller area network structure, or CAN bus.
Explain that for us. Why is CAN bus so perfect for a boat?
It's just designed for resilience. The NMEA 2000 network operates at a lower data rate, and it handles essential data: GPS position, engine RPM, wind speed, depth.
The really critical stuff.
The critical stuff. And its bus topology means if one device fails or gets unplugged, the entire network usually stays up. It's built for survival, not for speed.
That sounds like redundancy built right into the wire itself.
It pretty much is. Now, contrast that with marine Ethernet. Ethernet does the heavy lifting for high bandwidth data.
Like radar.
Exactly. Real-time radar images, high-res 3D sonar sweeps, video feeds. You need a big data pipe for that. But Ethernet is generally less resilient to vibration and connection issues.
So how do they deal with that?
You'll see dedicated marine-grade switches and these really robust waterproof connectors to try to mitigate those vulnerabilities.
So the two systems work side by side. One for bomb-proof stability with critical data, the other for speed with complex visuals. That's a clever architecture.
It is, and that architecture supports the four main pillars of onboard tech. Let's start with the one everyone gets: navigation and situational awareness.
Right. These are the eyes and the mind of the boat. They give you the real-time data you need to operate safely and efficiently, your position, heading, speed, depth, and what's around you.
And the central component here is the MFD, the multifunction display. The MFD is that single pane of glass that pulls together what used to be paper charts, separate depth sounders, GPS units, radar.
All into one scheme.
All into one manageable interface. And you have specialized tools that feed data into it, like radar for bad visibility, sonar to read the seafloor, and autopilots for efficient steering.
And what about redundancy? You mentioned that earlier.
Yeah, and that's a key point. On professional or even high-end leisure boats, these systems are networked across multiple helm stations.
So it's not just for convenience.
No, not at all. It means if the main display in the wheelhouse fails, maybe it overheats or there's a voltage spike, the captain can instantly get all the same data and control from a secondary station on the flybridge. That continuous data is crucial in bad weather.
That's a great link back to that engineering foundation. Okay, moving from awareness to interaction. The next pillar has to be communication and safety. These are literally life-saving systems.
They absolutely are. And this area is critical for compliance and obviously for emergencies. The foundation here is the VHF radio, specifically one with DSC functionality, digital selective calling.
What's the key benefit of DSC for the listener? Why is that so important?
It lets you instantly broadcast a distress alert that includes your unique vessel ID, and if it's hooked into your GPS network, your precise location. It's the difference between just shouting into the void and sending a digital location-specific SOS to the Coast Guard and every vessel around you.
And alongside that, you have AIS, the automatic identification system. That's like a digital handshake between vessels, right?
It is, yeah. AIS continuously broadcasts your boat's data position, speed, course, and it receives that same data from all other equipped vessels. It's just essential for collision avoidance.
Especially with big commercial ships, I imagine.
Oh, absolutely. Or in fog. The chart plotter can show you not just a vague radar blip, but the exact identity and intent of a nearby container ship.
And then the last resort, the emergency beacons.
Yes, the EPI Ares emergency position indicating radio beacons. They're designed to float free and automatically transmit a distress signal and GPS location via satellite. It gives you global coverage, even way offshore.
So far, we've covered the body and the voice of the boat, but none of it works without a steady heartbeat. So that brings us to our third pillar, which I think was a little undertreated in the original materials, power management.
Yes, this is the hidden, absolutely essential electrical foundation. We need to spend some real time here because this is where the biggest reliability problems come from.
So it's not just a battery.
God, no. Power management is this complex interplay of battery banks, inverters for your AC power, chargers, shore power hookups, and DC distribution panels.
But isn't 12-volt power inherently fragile, especially when you're trying to run a massive radar or big MFDs?
It can be, yes, which is why proper power management is so important. The sources all stress isolating your critical battery banks.
You mean having a separate battery for the engine?
Exactly. A dedicated house bank for your electronics and a separate start bank for the engine. It ensures that running your chart plotter all night doesn't leave you with a dead engine in the morning.
And beyond just keeping things running, there's a critical corrosion issue tied to the power system, right? Something called galvanic corrosion.
That is a huge so what for the listener. Galvanic corrosion happens when you have two different metals in saltwater that are electrically connected. If your bonding and grounding systems are compromised, you can just accelerate corrosion across the whole boat.
So you might see what? A propeller shaft just getting eaten away.
A propeller shaft, a transducer housing, any underwater metal. So bad power management doesn't just cause flickering screens, it can literally destroy the boat's structure over time.
Wow.
The dependence is absolute. Inconsistent voltage from undersized wiring or failing batteries leads to system resets. And you also have to manage parasitic draw electronics that drain power even when they're off.
Which is why you need those power monitoring displays.
You have to have them.
That makes it crystal clear why power management is its own pillar. Okay, moving to our final pillar, which is a bit more fun, but it needs the same level of resilience, marine audio systems.
Right. And if you think your car speaker handles a little humidity, just imagine a speaker getting hit with direct UV light, constant salt spray, and the physical battering of a boat.
Automotive parts would just disintegrate.
They fail in months.
Yeah.
The key differences are all in material science. Speakers need sealed cones, corrosion-resistant stainless steel hardware, and grills made from UV-stabilized materials so they don't get brittle and shatter in the sun.
If you see regular metal screws on a speaker, it's not marine grade.
Not at all. And it's going to bleed rust stains everywhere.
But the challenge is also acoustic, isn't it? You're fighting wind noise, engine rumble.
You really are. Practical experience shows that you need way more power and better speaker placement than on land. You need properly sized amps to overcome that ambient noise. And again, you need marine-grade, tinned copper wiring. Cutting corners here just guarantees you'll be replacing the gear next season.
Okay, so we've covered the individual specialized parts. Now let's move from the parts list to the operating system. how these things are wired together into a fully integrated platform. This is where it gets really important.
Modern vessels operate on synergy. The components aren't isolated anymore. They're constantly sharing data to maximize safety and efficiency. And that's only possible through robust networking like NMEA 2000.
Can you give us an example of that critical integration in action?
I think the best one is how situational awareness gets layered. GPS data feeds directly to the autopilot to hold a course. Radar images are seamlessly overlaid on the digital chart on the MFD. AIS targets pop up right next to their chart positions, sometimes even predicting a collision risk.
So it reduces the chance of human error.
Exactly, by centralizing all that information.
But the truly critical blueprint, the map of that whole integrated world, is the boat's electrical schematic. Define that for us.
The schematic is the detailed diagram. It documents exactly how every wire, every switch, every sensor, and every electronic system connects, interacts, and most importantly, how it's powered and grounded. It's the master plan.
If it's so vital, why do so many sources say that getting an accurate, up-to-date schematic is often a huge headache for boat owners?
That's a challenging but very realistic point. The lack of a good schematic often means a dangerous shortcut was taken somewhere, either during construction or a later refit.
Why is it so dangerous?
Because the schematic is what prevents circuit overloads. It ensures correct grounding and bonding to stop that galvanic corrosion we talked about.
And for the future, it must be invaluable for troubleshooting.
Oh, absolutely. Years later, when some specialized transducer fails, having the schematic means a technician can trace that fault instantly. They're not just guessing in a dark bilge.
So a good installer always provides one.
A reliable installer always documents the wiring layouts and schematics. It protects the owner, the boat, and the technician doing the repair.
That leads us perfectly into our final section, why professional installation is really non-negotiable. The contrast in lifespan is huge.
It's stark, and it speaks volumes about the environment. Professionally installed systems, the ones that follow standards like ABYC, they routinely last for 8 to 15 years.
8 to 15 years. And the counterpoint.
Improperly installed equipment, a DIY stereo, a poorly wired radar, it often fails within a single season.
Wow.
And it's not always that the component itself was bad. It's that the wiring fatigued or the connection corroded, or it just vibrated itself to death because it wasn't mounted right.
So what are those small details that a pro installer gets right that the average owner might miss?
It's really the execution of the fundamentals. Proper cable routing, so you're avoiding engine heat and high voltage interference. Selecting the right wire gauge for the length of the run to prevent voltage drop. And using marine-grade heat shrink connectors on every termination to make it 100% waterproof.
It sounds like any shortcut is basically fatal in this environment. So what are the most common mistakes owners make that lead to those single-season failures?
Mixing automotive with marine components is number one. Then using undersized, non-tinned wiring, skipping the electrical schematic, or worst of all, improper grounding and bonding, that just sets the stage for rapid galvanic corrosion.
So the big recommendation is clear. Treat the electronics as a single interdependent system.
Absolutely. Marine electronics have to be designed as a complete integrated system with a real architecture, not just a collection of cool gadgets you bolt to the dash. That initial planning and professional execution is the difference between 8 years of reliability and 8 hours of frustration.
So, to summarize the core message for you, the learner, marine electronics are tough, integrated, purpose-built systems. They span navigation, communication, audio, and power. And the electrical foundation, the tinned copper, the proper power management, the vibration resistance, that is paramount. And professional design is really the key to longevity in this brutal environment.
And the value here is confidence. Understanding these really stringent, purpose-built requirements lets you demand safety, effective communication, and dependable power from your boat. These systems are truly the technological backbone of safe boating.
And that leads us to our final thought for you to mull over. Our sources repeatedly emphasize that modern vessels depend entirely on these integrated electronic systems to operate safely, to see, to talk, and to steer. If we accept that this hardware is the operational backbone of a vessel, does that make the documentation of that hardware, the boat electrical schematic, the single most valuable item on board? What does the quality, detail, and accuracy of that schematic tell you about the future readiness, safety, and operational history of your platform years after the installation is complete? Think about that next time you look inside